guys, and welcome to a new video. In this video we are going to solve a rational integral. Again, this integral will be a complex integral. So we are going to solve the integral using complex analysis. So the integral we are going to solve is the following. Dx. Okay, so we call the integral I, and we have the integral from minus infinity to plus infinity of this function. We have 1 over x squared plus 1 and then all squared in dx. Okay, so again, as you probably saw in the video about in which we solved the other complex integral, the idea here is to consider the residual theorem, and we know that if we consider the following integral, so we have to consider the integral along a path that we call C of the integrand z squared plus 1 squared dz, where basically C is the following path. So we have to consider the complex plane. So this is the real axis and this is the imaginary axis, and the path C is basically the following. So we have this circumference, and then we have this path. So C is basically made up of this straight line and this semi-circumference. So we are considering the integral along this path, so we can split up the integral. So the circumference, the radius is r, so we have minus r and r, so the straight line is 2r, and we can split the integral, so we can split this integral into two integral. So the integral from minus r to plus r of the same function, obviously, plus the integral along this semi-circumference that we can call CR, for example, of the same function. So the idea is to consider this integral, and we know, as we saw in the video, on the latest video on the complex integration, we saw that if we consider r approaching infinity, we have that basically this integral becomes this integral, so the integral that we have to evaluate. And as far as this integral is concerned, this integral goes to 0 as r approaches infinity, because basically this term goes to infinity, so we have 1 over this term and all the integral goes to 0 basically. But we know also that this integral can be solved considering the residual theorem, and we know that the residual theorem basically claims that this integral can be solved considering the residues of this function. Basically, the point here is also that the poles of this function are not simple poles but are double poles. So here we have to be careful, because this integral will be 2 pi times I, and then we have to calculate the residues of the poles, of the double poles of this function in minus I, which is also a double pole, but it is outside the path. So because of this, this integral will be 2 pi I times the residue of the function, let's call it fz, in the pole I, which is a double pole. Okay, idea is to focus on this calculation, and we know that the residue of a function for a double pole is given by, so we can write that this residue is given by the limit for z approaching the pole, so approaching I, of the derivative with respect to z of basically z minus the pole squared times the function f. Okay, where the function f is obviously 1 over z squared plus 1 squared, but we know that we can write f also in this form, so we can consider z minus I times z plus I, okay, and then all squared. Okay, so this is our function, and we have basically to consider the derivative with respect to z of this product. So if we consider the product z minus I squared times f of z, we have that basically this term cancels, so we end up with just 1 over z plus I squared, and then we have now to consider the derivative of this function. So that means that we have to consider the limit for z approaching I of the derivative of z with respect to z of this function plus I, okay, this is I squared. So we end up with, if you calculate this derivative, you will end up with minus 2 over z plus I raised to the power of 3. Okay, so this is the final, this is the result of the derivative. Now we have to consider the limit for z approaching I, so that means that basically we have to put in this expression I in the place of z, so we will end up with minus 2 over I plus I raised to the power of 3. So we end up with minus 2 over 2I raised to the power of 3. So we get minus 2 over 8I to the power of 3. So here we get just 1 and 4, and then we have is just minus I, so this minus goes away and we end up with 1 over 4 times difference, and we know that this integral, thanks to the residual theorem, is 2 pi times I times the residue of the function for in z equal to I, and we said that that pole is a double pole, so we had to consider the derivative. So we saw that the residue is 1 over 4 times I, so we end up with here we get just 2, so we end up with pi half. So we have that the result of this integral is pi over 2, but we know that if we consider the limit for which r goes to infinity, we have that basically this integral becomes our original integral I, and this integral goes to 0. So that means basically that our initial integral will be I equal to pi half. So this is the final result.